Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't got a problem. Today we're going to learn about the layers of the atmosphere. So as you take a rocket ship and you go up and up and up and up, guess what? It changes. So let's talk about one important thing though before we get into too much detail. I want to talk about something called air pressure. We talked about that a little bit ago. It's S-U-R-E. Air pressure. Air pressure is, this may sound weird, but do you realize that there's billions and trillions and gazillions and moles of little tiny molecules, oxygens and nitrogens, and they're flying around all over us. They're moving. This, you're not going to believe this, but in the room that you're probably in, that oxygen, its velocity is 1,000 miles per hour. The little oxygen molecules flying at 1,000 miles per hour. And when it hits something like you, it produces pressure. Right? You can imagine something throwing rocks and rocks and rocks and rocks at something, that thing that it gets hit feels pressure. Now these are tiny, 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 tiny things, right? They're oxygen molecules, but it creates an air pressure. So on the Earth at sea level, the air pressure is equal to 14 pounds per square inch. Now think about that for a moment. Take a square inch, but an inch, about so far, right? Just, probably the length of the tip of one of your fingers. If that's an inch, that for every square inch, right, it's a square inch, S-I, square inch, there's 14 pounds. So go to the weight room and grab a 14-pound weight. That's a lot of pressure, isn't it? And when we talk about meteorologically stuff, there's high pressures and low pressures, where it goes not from 14, but maybe it's 15, or it's 12 or something like that. It doesn't jump to 25 or something like that. But when you have that, that changes how things happen. And that's important because now what we want to do is we want to talk about air pressure and altitude. So take a look at this graph right here. And you can see at sea level, it's, well, what units is it using? So when we talk about air pressure, I want you to sketch this graph. You can see Mount Everest right there. This compares pressure and altitude. So as you go up from the Earth, right, the pressure 14 at sea level. Now this is using a different unit, something called a millibar, and it's actually it's right around about 1,000 or whatever. So 1,000 at sea level, and then as you go up and up and up, you notice what happens to the pressure. It goes down and down and down and down, right, almost to zero when you get to the top. And what's happening is that the pounds per square inch is related to two things, one more important than the other. It's related to how many molecules of air are there. So as you go up and up and up, and you've probably experienced this, if you've gone to the top of a mountain, some of you know I used to live in the mountains of Colorado. I lived at 9,000 feet. Well, at 9,000 feet, and you guys look at the chart right here, when I was at 9,000 feet, we were at about 75% of the air that we'd say in Houston, literally. If I were to count up molecule, 1, 2, 3, I find 100 here in Houston, I'd find 75 at my home in Colorado because there is less air. Maybe you've noticed this if you've maybe gone to Colorado and you have a hard time breathing. That's because there's less oxygen to actually breathe. Interesting thing, by the way, about humans, though, is if we live at altitude for a time, we will produce more red blood cells, and we'll be able to breathe more easily. So people who live at high altitude typically adapt. Not everybody can adapt, by the way. That's another issue altogether. So air pressure. So as you go up, the air pressure goes down. And one of the consequences of that is that actually 90% of all of the air is 10 miles or below. So, I mean, if you go up to 10 miles, 90% of all the air, and the atmosphere extends way beyond 10 miles, is almost all the gas is at the bottom. It's, by the way, because of gravity, because the oxygen and the nitrogen and all the different gases, they're attracted to the Earth, so they tend to live closer to the surface of the Earth than towards the above part. So that talks about the layers. So important to note, as you go up and up and up, the air pressure goes down and down and down and down until it really is almost zero. So now let's talk about the different layers of the atmosphere. You've got this graph, or this table, if you will, in your notes, and I want you to fill it out. And we're going to start from the bottom. The first layer that's like at about, from 0 to 10-ish is called the troposphere. This is where we live. We live in the troposphere, and almost everything that we understand is in the troposphere. And notice that as you go higher in elevation, it gets colder. The squiggly line is, of course, the temperature. And the gap there is then called the tropopause. That's the one right above the troposphere. That's where it moves from troposphere to the next layer. The next layer is called the stratosphere. So that's the stratosphere. And then we move up until we get to what is about 50, and then we get the stratopause. And that's the gap. And notice again, we have another temperature change. Now it goes back down. And then that goes up and up and up and up. And then we get to the next thing called the mesosphere. And then we get to the mesopause. And then we get to the thermosphere. And then above that, by the way, we call that the exosphere, which is kind of like space. Now let's talk in some detail about each of these spheres, if you will. The thermosphere, we'll start with the troposphere. So what are some characteristics of the troposphere? By the way, it means turns over, region where there's air turnover. It's a mixing. It's kind of an area of mixing. This is raw weather is here. And notice it gets colder when you go higher. In fact, there's some numbers. You may not know this. It's 3.5 degrees Fahrenheit per 1,000 feet. So if you go up 1,000 feet, on average, the temperature is going to change by 3.5 degrees Fahrenheit. You may again know this if you've been to some mountainous region. The higher you go, the colder it gets. That's why it's crazy cold at the top of Mount Everest, even though it's actually relatively close to the equator. All right, and then we move to the stratosphere. By the way, in between this is the tropopause. And that's just like the barrier when we're starting to see the change. Now, something that's interesting in the stratosphere, and this may not make sense, is the temperature gets higher, or temperature goes up as you increase altitude. Has to do with what the gases are present, why this happens, and it's really a kind of an intriguing thing. And this is where we have the ozone layer. We talked about that in a previous segment, right? And that's interesting. And then we move to the mesosphere. Again, here the barrier, if you will, is called the stratopause. Now the mesosphere reverses, right? The temperature goes down the higher you go. It is the coldest part of the atmosphere. Getting to, so I forget how cold, super crazy cold. And as a note, we haven't really talked about this, but the balloons can't get here. So we have these things called weather balloons that we send up, and then we can use those and we have things attached to it. They're pretty awesome. It helps us to understand what's going on up there, but the balloons can't get there. It's actually the least understood portion of our atmosphere. And the temperature is going down the higher you get. And then we get to the, if you will, the mesopause. And then we get to the thermosphere. Now thermo, you probably know this, means heat. And so here the temperature goes up. And this is actually the hottest part of the atmosphere. And this is also where we have the aurora borealis, aurora borealis. So that if you go in the northern lights, they look like this. So they're amazing if you ever get a chance to see them. Now here's the interesting thing. The temperature here can be like crazy high, like 500 degrees or something. I don't know the exact temperatures, but it's super hot. So if you've got super hot gas, let's say that you're an astronaut or a plane guy, and you take your plane and you go up to here and you get out and it's 300 degrees. You think you would incinerate instantly. You know what happened? You'd freeze to death. What? Wait a second. It's 300 degrees and I'd freeze to death? Why? It's because we need to understand the concept of temperature. Now we're going to go a little bit later in another video that talks about this. The reality is because of the air pressure that we talked about earlier, that there's so few gas particles present that those gas particles, though they would be moving faster, instead of moving 1,000 miles per hour like we talked about earlier, they're going to be moving at 3,000 miles per hour. But there's so few of them that they don't have enough to keep you hot. Because temperature and energy are not the same thing. We'll talk more about that in a later video. I think it's important to understand that. So even though the temperature is higher, that doesn't mean that it's going to burn. I know it's weird. So the layers of the atmosphere. Houston, we got no problems because you guys are awesome. We'll see you in class.